Imagine spending like 3 weeks and $1 million training a massive language model, only to realize your loss curve has just flattened into pure garbage.
Yeah, an absolute nightmare.
Right. And you spend days debugging, assuming, I don't know, your data set is poisoned or your learning rate is off. But then you discover that your highly optimized AI-generated GPU kernel has been silently eating mathematical infinities and replacing them with zeros.
Just completely, quietly corrupting your training run.
Exactly. Welcome to AI Paper Slap, where we summarize AI and tech papers directly for the technical folks, the ML engineers and researchers actually building the infrastructure. Today, we are doing a deep dive into a paper titled A Contract-Grade Verifier for LLM-Generated GPU Kernels and a Native Blackwell Backward for the Gated-Linear-Recurrence family by Rishi Shah and Rishash Shrestha.
It is a phenomenal piece of engineering.
It really is. And we're going to give you the core insights straight out of the gate here. All those language models generating those incredibly fast GPU kernels with like super high reported correctness rates.
The ones everyone's rushing to put into production.
Yeah. Well, the benchmarks certifying them are essentially lying to us. They rely on these incredibly weak single-shape torch all-close tests.
Which miss almost everything that actually matters.
Exactly. So the authors of this paper built a strict 12-gate contract-grade verifier. And when they unleashed it on 2,638 supposedly correct AI-generated kernels, they found that nearly 40% were just fundamentally broken.
Broken as in swallowing NaNs or hard-coding tensor shapes, yeah.
Right. And furthermore, the authors proved this verifier actually works by turning it inward. They used it to build and verify their own native Blackwell TC-Gen05 training backward for the GDN family of models.
Which is a huge deal.
It is. They completely bypassed that notorious tensor memory limit bug that plagues the official implementations. So our mission today is to break down exactly how AI kernel generation has been faking it, how this new verifier works, and how they achieved a first-of-its-kind native Blackwell kernel.
I mean, the implications of this paper for the whole ML ecosystem, they really just cannot be overstated. We are currently seeing this massive explosion of excitement about LLMs writing optimized CUDA in Triton code. Right?
Oh, yeah. Everywhere you look on Twitter or GitHub.
Exactly. Companies are just rushing to integrate these kernels into their production pipelines to squeeze out, every last ounce of performance. But the foundation that excitement is built on.
The test harnesses.
Yeah, the test harnesses that assure us the code actually functions as intended, they're completely crumbling under scrutiny here.
So we need to unpack how the entire field got tricked in the first place. I mean, now that we know nearly half of these so-called correct kernels are actively broken, the first question is, what exactly is the standard acceptance signal missing?
Right, like what are they testing?
Yeah, like if I'm an ML researcher and I just used an LLM to generate, say, a custom Triton kernel to replace a standard PyTorch operator, I'm going to run it through a standard benchmark, right? Like KernelBench or TritonBench.
And those benchmarks almost universally rely on a torch.allClose test. Under the hood, this involves taking your candidate kernel and running it against a slow, trusted reference implementation.
Okay.
The harness draws a few random inputs, usually at just a single fixed tensor shape. And then it checks if the output tensors from your kernel are numerically close to the reference, bounded by some arbitrary absolute and relative tolerance.
Like, what, 10 to the minus 2 or something?
Exactly, like 10 to the minus 2. And if the numbers fall within that completely arbitrary window, boom, the kernel is stamped as correct, and the benchmark just moves on to measuring how many microseconds it takes to run.
Wow. I mean, that sounds somewhat rigorous on the surface, but mathematically testing a single shape with an arbitrary tolerance is just a massive blind spot.
Oh, it's huge.
Like if a generated kernel happens to hardcode a sequence length of 128 and the test just happens to pass in a tensor of size 128, the kernel looks like a genius piece of engineering. But then you deploy it, feed it a sequence of length 256, and it immediately seg faults.
Right, crashes instantly. But, the single shape issue is bad, but what the paper outlines regarding precision loss and statefulness is actually far worse.
Really? How so?
Well, a kernel can easily pass that torch.allClose test while secretly accumulating its internal reductions in float 16. So it's losing critical precision along the way, while the reference implementation is safely using float 32.
But because the test harness uses that loose tolerance you mentioned.
Exactly. The precision drift flies completely under the radar. Or consider determinism. You can run the exact same AI-generated kernel with the exact same inputs twice and get two slightly different outputs due to, race conditions in the thread blocks.
Oh, yikes.
and it'll still pass the test because both of those outputs just happen to land within that 10 to the minus 2 threshold on that specific run.
Which means torch. All close isn't actually checking if the logic is sound at all. It's just checking if the output isn't completely catastrophic on, like, a single sunny day.
That is a perfect way to put it.
It's essentially like buying a used car and testing the engine by just checking if the paint looks good from 10 feet away. You're entirely ignoring whether the engine actually runs when you turn the key or, if the steering wheel falls off when you turn left.
Right. It looks like a car, but it doesn't function like one when you need it to. And the stakes for production machine learning here are just catastrophic.
Yeah, I can imagine.
Engineers are ripping out stable PyTorch code and dropping in these LLM-generated kernels based entirely on these illusory benchmarks. We aren't actually getting faster, correct code. We're deploying code that fails silently, corrupting state and gradients at scale.
So building a real diagnostic tool, a theoretical lie detector to catch these kernels, brings us to the core thing developed in the paper, which is this 12-gate contract-grade verifier.
Right, they didn't just tweak the old tests.
No, they didn't just tighten the tolerances. They operationalized a taxonomy called kernel contracts into 12 adversarial gates, and a candidate kernel must clear every single one. I want to break down how they engineered the first type, which are the thresholded gates, like ORD01 for reordered summation.
Yeah, so the key innovation with the thresholded gates is the total elimination of arbitrary guessing. The verifier derives its tolerances mathematically from actual floating point error accumulation models.
Meaning they don't just pick 10 to the minus 2 out of a hat.
Exactly. In a reduction operation, like summing up a massive matrix, the floating point drift isn't static. Error accumulates proportionally to the square root of n, where n is the number of elements being processed.
Okay, that makes sense.
So as your tensor grows, your allowable drift actually has to scale dynamically. The verifier calculates this exact mathematical bound on the fly. The threshold is tailored to the specific operation and input size, leaving no room for a kernel to hide sloppy float 16 accumulation behind some generous static tolerance.
Wow. And then the second category of gates is where the paper completely changes the paradigm, right? The tolerance-free gates.
Yes, these are crucial.
These are gates like EXCs01 for exception handling, CMPs03 for shape variations, and OROD02 for determinism. When I look at this from a purely engineering perspective, tolerance-free gates just feel non-negotiable because they rely on exact byte or mask equality.
There is zero wiggle room.
Right, there is no mathematical argument to be made. If the reference implementation produces a NaN, not a number at index 5, and the candidate kernel produces a 0.0 at index 5, no ML researcher can argue about precision thresholds. There is no tolerance universe where 0 equals infinity.
No, exactly. Completely removing that human subjectivity is the most vital step. A kernel either manages memory and exceptions identically to the ground truth, or it is broken, period. But, the authors also had to ensure the verifier itself wasn't cheating or, introducing false positives through sheer adversarial randomness.
How did they manage that?
They implemented really strict controls for the testing harness. Before drawing inputs for any gate, the verifier reseeds the random number generator from a fixed deterministic value.
Oh, smart.
Yeah, so the verdict depends strictly on the kernel's logical architecture, not on just getting a lucky or unlucky matrix of inputs.
Plus, the reference implementations they use as the ground truth are fascinating. They are defined as these slow, high-precision loops that literally refuse to run in reduced precision.
Right, they force an upcast to float 32 or even float 64.
Exactly. It guarantees that any ambiguous discrepancy sides with the candidate kernel. The verifier essentially bends over backwards, to be fair, which honestly makes the audit of the AI-generated code that much more devastating.
Oh, it was a bloodbath. When they pointed this mathematically sound verifier at the field's most celebrated AI-generated code, the results were just brutal. They audited the Dr. Kernel, or Kernel GYM corpus, which is a widely used public data set of AI-generated Triton kernels.
Okay, so this is the good stuff.
Yeah, the authors pulled 2,638 kernels from this corpus. And keep in mind, these are kernels the original system's harness had already tested, timed, and stamped as 100% correct.
Right. And when they ran those 2,638 correct kernels through the 12-gate verifier, 62.1% carried at least one contract violation.
Just staggering.
It is. And I really want to pause and digest the floor here. The tolerance-free failure rate. A massive 39.5% failed a tolerance-free gate. That is 1,043 kernels.
Yep.
If I am a systems engineer pulling code from these repositories to speed up my pipeline, 4 out of every 10 kernels I grab are broken beyond any subjective tolerance argument.
It's terrifying. Let's dig into the specific mechanics of those failures, though, because the modal defect is just a nightmare for anyone actually training models.
Let's hear it.
The highest failure rate belonged to the EXC01 gate, which checks for non-finite non-propagation. It had a 34.2% failure rate. This is NaN swallowing.
Oh, man. Going back to our analogy, NaN swallowing isn't just a broken car engine. It's like a fire alarm that detects smoke and decides the best course of action is to secretly unplug your thermometer so the room reads as a comfortable 72 degrees while the house burns to the ground.
That's exactly what it is.
If you get an exploding gradient during a massive training run, a normal system propagates that infinity forward. It ruins the loss, the training loop crashes loudly, and you immediately know you have an instability to fix. You can step in.
Right, it screams at you. But these AI-generated kernels, they encounter that exploding gradient, quietly replace the infinity with an ordinary finite number like 0, and then just feed it to the next layer.
That's so bad.
The training loop doesn't crash at all. It just keeps updating weights based on fabricated numbers. It converts a loud, easily detectable training time error into totally silent data corruption.
Wow.
Your model is poisoned from the inside out, and you have zero visibility into why it's outputting complete hallucinations weeks later. I mean, it is the absolute worst-case scenario in ML engineering.
Okay, I have to push back here on behalf of the skeptical ML engineer listening to this. The immediate counter-argument to a 60% failure rate is that the verifier is just, I don't know, obnoxiously strict by design.
Sure, the too harsh argument.
Yeah, exactly. If I build a metal detector and crank the sensitivity so high that it beeps at the iron in the dirt and the zipper on my jacket, I will undoubtedly find all the buried treasure. But I am also going to dig up a mountain of trash. How did the authors prove they haven't just built an overly sensitive detector that just fails foreign kernels by construction?
That is a very fair question, and the authors anticipated that exact objection. They actually built 4 independent, falsifiable defenses to prove their verifier's fairness.
Okay, lay them out.
The first is a positive control. They took 7 of their own handwritten, heavily optimized Mamba 3 kernels and ran them through the exact same 12-gate battery. All 7 passed perfectly.
Oh, nice.
But the crazy thing is, during that development process, the verifier actually caught a catastrophic bug in their own C5 fused block forward kernel.
Oh, wait, the shape rigidity bug. Right, I read that section.
Yes.
The kernel was dynamically inferring its channel dimension directly from the input tensor without validating it against the convolution weight channels. It was completely missing an input validation guard.
Exactly that. And the verifier flagged the missing guard, the authors fixed it with a one-line validation check, and then it passed. The fact that the tool bit its own creators, forcing them to write safer code, is really strong evidence it isn't just tuned to flatter their own programming style.
Right, it's actually catching real logic flaws. What's the second defense?
Second defense deals directly with those thresholded gates. They performed a threshold calibration sweep, where they injected mathematical perturbations of known magnitudes into known correct operators.
Like intentionally introducing noise.
Exactly. And they mapped it out and proved that for every single thresholded gate, there is a massive, clean separation between the honest floating point noise the correct kernel emits and the actual error a broken kernel emits. The thresholds sit perfectly in that mathematical margin between right and wrong.
That's super rigorous.
Yeah. And the third defense neutralized the argument that they just wrote a faulty replica of the standard checks. They achieved 98.5% agreement with KernelBench's own baseline correctness code.
Oh, so they didn't break the old test.
Right. They ran the original benchmarks code alongside theirs to prove their verifier correctly identifies what the old standard identified. It just identifies much more on top of it.
Which brings us to the fourth defense, the differential. And this is honestly the mathematical kill shot for the too strict argument.
It really is.
If you look at the delta between the two testing paradigms, KernelBench's standard test accepts 1,487 kernels that this new verifier firmly rejects.
Right.
But if you look at the other direction, kernels that KernelBench rejects but this new verifier accepts, the number is only 14.
A unidirectional differential of 1,487 to 14 is just profound.
Yeah.
If this were merely a subjective disagreement about strictness, where the new verifier just draws a slightly tighter circle, you would expect a much wider spread in both directions that edge cases just bounce across the boundary line.
Like a Venn diagram with a huge overlap, but big independent sides.
Exactly. A near unidirectional disagreement of that magnitude is the signature of a systematic blind spot in the original acceptance signal. It proves beyond a shadow of doubt that the standard test is structurally certifying broken code.
Okay, so building a theoretical lie detector is one thing, but to prove it actually works, you have to run it against real bleeding-edge hardware limits, which brings us to the nightmare that is the Blackwell B200 tensor memory constraint.
Oh yeah, this is a whole other beast.
The authors aim their verifier inward to build a native backward pass for the Gated-Linear-Recurrence, or GDN family, and this covers Mamba 2, GLA, DeltaNet, KDA, and linear attention. Because roughly 80% of the parameterization is shared across these architectures, one generalized backward pass yields the training gradients for all 5.
Which is incredibly efficient. The heavy lifting of that backward pass relies on 2 mathematically brutal stages. First is KSHAC-1, which is the reverse interchunk state scan. This is a sequential reverse time walk that accumulates the state gradient backward across memory chunks. It is notoriously hostile to parallelization, which is why most open libraries still rely on a really slow Triton fallback for it.
And the second stage?
The second is KSHAC-2, the WI, or triangular inverse vector Jacobian product, which is honestly just dense, nasty matrix math.
But the math isn't what's breaking deployments right now, is it? It's the hardware.
Yes, the hardware constraints are brutal.
Right. For anyone tracking the rollout of the Blackwell SM100 architecture, bug #904 on the Mamba GitHub is basically legendary at this point.
Oh, absolutely.
The Blackwell generation introduces a new tensor core, the T-STIGN-05, and requires operands for matrix multiplies to reside in a deeply scarce on-chip space called tensor memory, or TMEM, and the hardware enforces a strict hard budget. A warp group can utilize exactly 512 columns of TMEM, not a single column more.
And the official Mamba 3 backward pass compiler requests 544 TMM columns.
So it's literally trying to park a bus in a compact car spot.
Pretty much.
It attempts to compile, the hardware rejects it, it yields illegal machine code or deadlocks, and it instantly fails.
Which forces the system to trigger a fallback to an unoptimized Triton path that has been benchmarked as nearly 40 times slower on Blackwell.
40 times slower.
Yeah. So the authors of this paper analyzed the failure and diagnosed it as a memory lifecycle error. The official compiler implementation was trying to reserve the full TMEM budget and release it sequentially for every single matrix multiply.
Oh, I see.
The overhead and fragmentation of constantly claiming and releasing that memory just exceeded the architectural limits.
So to bypass this, they implemented what they call an alloc once, relinquish once with offset partitioned accumulators lifecycle.
It's a mouthful, but it works.
Yeah. Physically, in terms of GPU memory, this means instead of letting the compiler naively ask for memory over and over, they grab a single contiguous block of TMEM at the very start of the kernel. They hold it. Then they use manual pointer math to slice that block up for the different accumulators needed during the matrix multiplies. They manage the offsets entirely by hand, stay under the 512 column limit, and release the block exactly once at the end.
It requires an immense amount of manual, low-level engineering, but it completely sidesteps the compiler's fragmentation issue.
That's brilliant.
It allows both KSHAC-1 and KSHAC-2 to finally run natively on the T-STIGN-05 tensor cores. Now, to be fair, the authors are highly transparent about their current performance. Their native kernel is structurally slower right now than the highly optimized Triton flash linear attention library.
Why is that?
Primarily because their generalized version executes in sequential reverse time, while the Triton library kind of cheats by reusing inverse data saved from the forward pass.
Got it. But raw speed isn't actually the victory here, is it? The victory is that the kernel is native to Blackwell. It generalizes across 5 distinct foundation models, it is rigorously mathematically verified, and it completely bypasses the #904 compile failure. Which forces us to ask, how do we know these two halves of the paper actually connect? How do we know this custom Blackwell kernel isn't just, a separate flex attached to a verifier paper?
That is the best part. The connection between the two halves is probably the most elegant part of the whole research. The authors actually map this out in the paper, showing that the exact properties breaking the foreign AI code are the exact constraints that challenge their native kernel.
Give us an example.
Well, for example, the RESO2 gate in their verifier is specifically designed to check if compiled kernels respect real hardware execution limits.
Okay.
That gate maps 1-to-1 with the hashtag 904 tensor memory bug they had to manually engineer around.
Oh, wow. And the alignment with the EXC01 NaN swallowing gate is even more direct, right?
Yes.
We discussed how 34.2% of the AI-generated kernels failed because they quietly replaced NaNs with finite numbers. During the manual development of this Blackwell backward pass, the authors encountered a severe bug involving an exponent overflow from a masked XP2 function. It was generating infinities.
And the only reason the authors caught that exponent overflow was because their custom kernel strictly adhered to the contract of faithfully propagating NaNs.
It actually crashed like it was supposed to.
Exactly. The match blew up, the infinity propagated cleanly to the loss function, the training loop crashed loudly, and they were able to trace the stack, isolate the masked XP2 function, and actually fix the numerical instability.
The asymmetry there is just incredible. The authors only succeeded in building a working, bleeding-edge hardware kernel because they mathematically enforced the exact property NaN propagation that the LLM-generated kernels actively failed.
Yes.
The AI kernels survived the benchmarks only by hiding their bugs. This proves the 12-gate verifier isn't just grading harshly on some abstract academic scale. It is strictly enforcing the non-negotiable properties required to write, debug, and deploy real systems software.
It really is. The ultimate takeaway for the ML field here is that our reported progress in LLM-generated GPU kernels is heavily inflated by subjective, inadequate testing. Until the industry adopts tolerance-free contracts as a baseline benchmark standard, every claim of a faster AI-generated GPU kernel needs to be met with intense skepticism.
Agreed.
If a kernel isn't rigorously checked for state corruption, sequence length rigidity, and NaN propagation, you aren't doing engineering. You're just generating fast, silent data corruptors.
Which leaves us with a pretty chilling, forward-looking reality to mull over.
Oh yeah, it gets worse.
Right now, we are using LLMs to write code that silently corrupts data.
Right.
And it is making its way into production because our human-written tests are fundamentally too weak to catch the errors.
Right.
But what happens when we take the human out of the loop entirely and we start using these same LLMs to write the tests and the benchmarks for the next generation of models?
That's the scariest part.
Yeah, who's going to verify the verifier?